1.6, limits at infinity. So limits at infinity are basically written like this. Limit as x approaches either positive or negative infinity of the function. So we're trying to observe. I'm going to look at the graph for right now. We're trying to figure out what's happening to the graph as it gets closer to infinity or negative infinity. For the graph right here, I'm going to look at both. Okay, so in this direction, we're headed towards positive infinity, right? These numbers are just going to get bigger. And in the left here, these numbers are just going to get more and more negative, which is smaller. So what I want to do is I want to look at the end behavior of the function. So basically the end, this part right here. Where is that headed towards? Now, the where is the y value, and this is where people get confused. I'm trying to see how high or how low my function is at the end there. Okay, so observing this graph, I can tell you that it appears that it tops out at y equals 3 whenever I'm headed towards positive infinity. So my answer would be 3. Now for the left, it's actually the same. This function is symmetrical. It's doing the same thing on the right and on the left. So if I were to have had this written out, the limit as x approaches negative infinity of f of x, then my answer would also be 3. Okay, so that's just for this function right now. Numerically, if I go down to this table, it's basically the same idea, only that instead of trying to figure out where it's headed towards somewhere in the middle, like before, I'm looking at the ends. And then so here, I'd be headed to negative infinity, and on the right side, I'd be headed to positive infinity. But you're still looking at the table itself. So headed this way, okay, what's happening? So it was 0, 1.5, 2.97, 2.9997. I mean, it's just getting more and more closer to 3. On the right, as it's going to the right, what's happening? Same thing. Okay, so graphically, numerically, you can also do this algebraically. Here are some of the rules for algebraically. Limits at infinity of polynomials. Polynomial, okay, so like this. Well, let me make this cubed. I'm sorry. Let me do this over. Oh, it's so sloppy. Why won't it erase? There we go. Okay, so 3x to the third plus 4x squared plus 3x plus 9. Whatever. Made it up. Okay. So here's a polynomial. And it's saying that if I were to actually be looking for the limit of this function, let's go with positive infinity for right now, that as long as my highest degree, which I wrote this in order, so this is the highest degree, my biggest exponent, right? As long as it's a positive integer, which 3 is, then my limit is always going to be headed towards positive infinity. Now, down yonder here, student blue, it gets a little more technical. It's saying that if n, which is supposed to represent the integer, not the integer, oh my god, the exponent, if n is even, so if the exponent is even, and now we're headed towards negative infinity, then for an even function, we're still headed towards positive infinity. So, in other words, if I were to change this and now this were negative infinity, and my exponent had it been an even number, then, which I did just change that to a 2, right, people? Forgive me for this. Well, actually, let's change it to a 4. That's why it's the highest exponent. It's an even number, so my answer is still positive infinity. But, let's undo that. Let's undo that changing to a 4. Okay. But if n were odd, such as it was when I started this, my exponent was 3, and I'm approaching negative infinity, then my answer is actually going to be negative infinity. And you can see this by looking or analyzing graphs of functions. So here's x squared, right? X squared is totally even. Here's x cubed. X cubed is totally odd. As you can see, The end behavior, right, for an even function is, oh, look, it's headed towards positive infinity, right? That's what this is saying. For even, it's positive infinity, no matter what, basically. Now, for odd, let's do this in purple. For odd, end behavior as x is getting bigger and bigger and bigger and bigger, the end behavior is um, positive infinity. Y is getting bigger and bigger and bigger and bigger. But as x is getting smaller and smaller on the other end, y is getting smaller and smaller, so negative infinity. So this is easy to remember if you can remember these two graphs. Okay. So let's try it out. Find each limit. A, the limit as x approaches infinity of x cubed. So this is an odd exponent, but it really doesn't matter because we're headed towards positive infinity, so it's always really going to be positive infinity. Now, this limit technically does not exist, but I can actually tell you if it's infinity or negative infinity, because it could be either. And sometimes you have to know which one it is. Does not exist is not good enough. Right. B. So my exponent, the highest degree is an odd number, and I'm headed towards negative infinity. So since it's an odd number, and I'm going towards negative infinity, then my limit is negative infinity. Because like a fifth root function is going to look something like, let's see, 1, 2, 3, 4, 5. It's going to look something like that. Right, C. C is tricky, and the reason C is tricky is because of this negative. That negative automatically flips this function. So for example, a cubic is normally like this. Yes, hopefully. That negative makes the cubic now look like this. So it changes the end behavior, right? So you have to keep that in mind. So basically, when you're finding the limit, you could just like leave the negative for the end. So here's negative, and then whatever my answer is. And so that way I'll make sure it changes it. So back to the rules from the previous slide. My exponent is odd. I'm headed towards negative infinity. So if my exponent is odd, and we're headed towards negative infinity, my limit should be negative infinity. But then I remember, oh yeah, there was this negative in the front of my function here. So that's why I put it here. And look, negative times negative. So now I just have one big fat positive infinity. Okay? All right, D. My exponent, my highest degree is 4, which is even. So positive infinity. All right, horizontal asymptotes. I'm going to sketch something real quick. Right, here's my sketch. This function appears to have a horizontal asymptote right about here. Okay, maybe if my line were better. Let me redo that. Oh boy. Right about there. That's a little better. Now, what I'm trying to prove with this is horizontal asymptotes don't work like vertical asymptotes. Functions do not pass vertical asymptotes. They are a break in the graph, and they don't, go through a vertical asymptote. But graphs are allowed to go through horizontal asymptotes. I wanted you to be aware of that. Such as my horrible picture here. My function does actually cut through the horizontal asymptote right here. But it is obvious, hopefully, that towards the end here, the horizontal asymptote is taking effect in this function, and that's why it is a horizontal asymptote to begin with. And so that's just like a little fact that I kind of need you guys to know. Alright, so beyond that now. Here are the rules if I have rational functions. And rational functions are basically, oh my goodness, so sloppy. This, right? A ratio. A bunch of stuff on top, bunch of stuff on bottom. Polynomial on top, polynomial on the bottom. Now these rules are like shortcuts. They can tell you what the limit is, as long as you figure out what the asymptote is. I have a key over here. I'm telling you that m and n are integers, which just means that they're numbers, positive, negative, or 0, right? But m is bigger than n, so m is the bigger number. So like for the first part here, I have a ratio, and my exponents are exactly the same. When my exponents are the same, my horizontal asymptote is going to be located wherever these two numbers in the front here get me. All I got to do is take a ratio of the coefficients, a and b, and whatever that is, that's where my horizontal asymptote is located. Y equals a over b. Okay, now for the next one. Whenever the bottom, the denominator, has the bigger exponent, and I like to call this bottom heavy just because the degree on bottom is bigger. This is not a mathematical term or anything. Your horizontal asymptote is located at y equals 0, and then therefore your limit um, as x approaches infinity, positive or negative, whatever, is going to be 0. Okay, the last one. The top is heavy, right? So I call this top heavy. This is just a way to remember it. No, nothing else. This is not any special code word. When it's top heavy, there is no horizontal asymptote. I like to look at this as, ooh, I can actually divide this. Like the top one is bigger, therefore I could actually do synthetic division if needed or whatever. And so that's a way I remember it. There is no horizontal asymptote because there is an oblique asymptote instead. Now for here, the limit would not exist. There would be none. Okay. Next. Example 3. So here we're going to put those to use. For the first one, this is the same as splitting it up. It's like the same as looking at it like this. The limit as x approaches infinity of 5 minus the limit as x approaches infinity of negative 2 over x squared. Same thing. Or, I'm sorry, I already minused it. I don't need this negative. Erase negative. Okay. I erased more than the negative. Oh boy. So 2 over x squared. Okay, so it's the same thing. If I do the front part, let's see, the limit as x approaches infinity. Ooh, I have nothing to plug the infinity into, therefore it is just 5. But for the latter part here, I can use my horizontal asymptotes. This is bottom heavy, right? And all you gotta do is, well, you gotta look up on your paper. But when it's bottom heavy, oh yeah, 0. So this is 0. So 5 minus 0 is 5. And there's my limit. My limit is 5. Okay? B. All right, B, the fact that this has a negative, so like I want especially specifically the limit as x approaches negative infinity, it changes my horizontal asymptote thing. I could use the horizontal asymptote because this is top heavy. And top heavy means there is none, so it doesn't exist. Well, whenever we get infinity or negative infinity as a limit, the limit always doesn't exist because what is infinity? But sometimes they do want you to specifically tell them which one of these two your answer is. And that requires a little bit more work. And this is how you're going to do that. Okay, you're going to do a little bit of algebra. You're going to take the top, right, and the bottom. I'm sorry if you don't have enough space for this. And you're going to divide by the biggest x term in the denominator. So in the denominator currently, I just have 1x. So we're going to divide everything by x. If it had been x squared, if this had been x squared like that, we would divide everything by x squared. Okay? Right. So a little bit of algebra, and please try to squeeze this onto your paper. So x cubed divided by x is x squared. 8 over x is just going to stay exactly like that. I can't do anything with that right now. X over x is 1, and then the 4 over x is going to stay. Now by doing this, I can use my horizontal asymptote rules. Okay? Um, and the parts I'm going to use it on are here and here. These are bottom heavy. And for bottom heavy, oh yeah, remember here? It equals 0. So now this is basically x squared minus 0 over 1 minus 0. So now I can go ahead and plug in the negative infinity. You're like, what? We're plugging in negative infinity? Yeah, I know. Not really. But for x squared, if you need to go, I don't know, to the top of your page to see what happens when it's a even function, right? It's an even function, and we're going towards negative infinity. Hopefully you can answer that for yourselves, right? But it's just going to be infinity. Oop, infinity, right? So it's infinity minus 0 over 1 minus 0. So infinity. See, the is okay, but sometimes you actually need to tell me which one of the infinities this is headed towards. Because does not exist usually means yes, it's headed towards infinity, in which case we don't know what that is, therefore it doesn't exist. A limit does not exist because it is unlimited. But sometimes I actually need you to tell me, well, was it headed towards infinity or was it headed towards negative infinity? All right, example 4. Find the limits at infinity by finding the horizontal asymptotes of each function. So here, I started off with just, infinity, infinity, but then I have a negative infinity back here. So find the limits by just using the horizontal asymptotes. All right, this square root, you must be like, oh my god. Just think of a square root as an exponent of 1/2, because that's what a square root is. And so now I have x squared on bottom. This is bottom heavy. Okay, bottom heavy means the limit is located at y equals 0. So my answer is just 0. Okay, that's all you gotta do. You just gotta play with it. All right. B. The exponents are the same, so therefore I just have to take the ratio of the coefficients, 6 over 4. And that's perfectly fine. You don't have to simplify it, but I'm a creature of habit, so 3/2. For C, it is top heavy. That means I can actually divide this. Oh yeah, that means there is none. Does not exist. But where, maybe? Like, doesn't exist. Great. But could you figure out, is it a negative infinity or positive infinity? So we're going to do the exact same thing I did in the previous example. It's not a bad thing to learn. All right, so 2x cubed plus 5, and then 3x squared plus 1. And then we're going to take the biggest x term in the denominator, which is x squared. X squared. Divide everything by x squared. I can do that, right? Because math. These cancel out. So what am I left with? I'm left with 2x plus 5 over x squared, which we're going to leave, oops, that's a 5, not an x, which we're going to leave just like that, over 3 plus 1 over x squared. So remember, the top or the bottom heavies become zeros. So this is 0 and 0. So now I have 2x plus 0 over 3 plus 0. So now it's kind of like you're plugging in, right? My x was supposed to be approaching negative infinity. So this is just going to be negative infinity. You can use the rules of polynomials. This has a degree of 1, which is odd. And for odd functions, as it's approaching negative infinity, it's negative infinity. And then divide by 3. But see, the thing about infinity is even if you divided it, it's still infinity. So there you go, negative infinity. All right, that's it. Answer the practice problems, please.